Thank you very much. It's a privilege to be here. This morning, you had the opportunity to hear the word Healthspan talked about quite a bit. General Hammond started out earlier today talking about the what with Healthspan. And you just heard a great talk from Dr. Bonvi about the why Healthspan in particular is so important when it comes to operators. I'll be talking a little bit about the nuts and bolts of the how, along with my colleagues, Dr. Mata and Dr. Tanev, a little later this afternoon. So I don't have any disclosures that are particularly relevant to this talk. I get some money from the NFL Players Association. But we just heard about how soft personnel are incredibly unique. They experience some of the most extreme exposures that are possible, the extreme limits of human endurance and performance. And these unique exposures result in unique sequelae that warrant an integrated approach. And what we're trying to do is to better link all those different ideas together to identify which exposure factors are related to maladaptive health patterns later, so that we can better understand how that affects people's chronic disease burden and their risk of problems later in life, including impairments in health span, which, as you heard, are years spent free from chronic disease, injury, and burden. So let's talk briefly then about what exactly is going on in response to these types of exposures from a neurologic standpoint. So this is a cartoon of a brain cell. And going back to, for those of you that aren't in the medical space, the high school biology, we have an electrical signal that's converted into a chemical signal to convert information and transmit it from cell to cell. Now, after an injury, there's a disruption to that cell. The cell is stretched in such a way that it can't control the signals and the way that they're being processed. What that means then is you have this massive efflux of potassium from the cell and influx of calcium into the cell, and that causes unregulated firing of the cells. Now, when you think about the brain cells are, your brain is about 7% of your body's total weight, but it's responsible for over 20% of the energy utilization in your body. And that's under normal circumstances. Per gram, your brain is using more energy than even your muscles when you're working out your hardest. That's when things are going normally. Now, in this system where there's an injury, where there's this unregulated firing of the brain cells, there's an energy crisis because your brain cells are using even more energy than they usually need. And they can't get the nutrients they need to sustain that level of higher burden. Now, in the vast majority of cases, this process resolves and goes back to normal. But we're going to talk about what can go awry. So when you're trying to track what's going on with brain cells, when we're trying to understand how to determine who's at risk of having problems later in life, there are a bunch of different biomarkers in our blood and in our CSF and in other ways that might indicate that the neurons are not working the way they're supposed to be working. There's neuroinflammatory markers, there's cell death markers, there's markers of different damage to different parts of the cells. But when we look at these biomarkers, we find in general, they don't work too well in terms of identifying who's got a problem and who doesn't. And I list some of the reasons here for why biomarkers don't work so well, but I think the biggest and most important reason is this last one, where we're calling injuries to brain tissues things that result in symptoms immediately after the injury. And when we look for biomarkers, when we look at markers of cell damage, cell injury, a lot of times they are elevated after impacts that aren't causing symptoms, after impacts that aren't causing things that we would consider injuries. And I'd like to take a hiatus away from the military space into the sports space for a second. So over the last 20 years, we've utilized a number of different technologies to track in real time helmet sensor information from athletes to better understand the impacts they're receiving to the head. And based on these helmet sensor data, we can track, for example, an average offensive lineman and say, for that lineman, if that lineman gets a concussion, we can go back and look at their previous history and see that on average, for every concussion that that person experienced, if that concussion is this green helmet here, they experience on average 341 head impacts that are equal or greater force than the head impact that resulted in the concussion. And the reason that our biomarkers, I think, haven't been working so well, the reason that our indicators of neurologic injury haven't been working so well is because they're picking up all those dark blue helmets. They're picking up all those head impacts, regardless of whether they're resulting in symptoms, regardless of whether or not we're currently treating them as injuries. And so in part, what I think we need to do is reframe how we're thinking about these impacts and injuries to better understand the long-term effects associated with them. So we published a paper in the British Journal of Sports Medicine earlier this year where we looked at reframing the terminology related to impacts and injuries. And when discussing impacts, there's this term called subconcussive impacts. And that's like a really fraught term because when you think of subconcussive, you think that they're less than the impacts that cause the concussions. But I just showed you, 341 of them are of equal or greater force. We propose we should be calling them non-concussive impacts. There are concussive impacts, and there are these other impacts, some of which may be causing injuries and some of which may not be. And so when we're talking about injuries, rather than using a catch-all term like subconcussive to describe both the impacts and the injuries, we need a new term. We need to borrow terms from neurology where there's this idea of for example, for stroke. You can have a stroke that doesn't result in any symptoms, but after many of these, I scan your brain and I can see evidence of all these strokes that have occurred over time. And that increases your risk of vascular dementia, increases your risk of problems later in life, increases your risk of having impairments in Healthspan. Those strokes are called subclinical strokes. We need to be talking about brain injury in the same way as subclinical traumatic brain injuries. And these are the things that our biomarkers are likely picking up. So what can happen then after accumulation of these subclinical traumatic brain injuries? So this is another cartoon. I'm going to blow up the top left portion. And this is another image of a brain cell. Now, the brain cell has this beautiful and complex cytoarchitecture. You think about your neurons, they can be some of the biggest cells in your body, extending from your brain down to the bottom of your spinal cord. What supports that complex cytoarchitecture are these scaffolds of microtubules, one of which is blown up here. The microtubules, if you think of them, like I said, as the scaffolding, they support that structure, and what supports the scaffold are depicted in purple here as a tau. That tau it's like the nails that support the scaffold. Now, in a number of different neurodegenerative processes, these nails can run into issues. So I'll blow up this portion here. In a number of neurodegenerative processes, those tau filament proteins can have a phosphate group attached to them that causes them to bend in shape. Basically, the nail's getting kinked. And that'd be a problem for the scaffold if you had one nail bent. But the problem is that those bent nails can induce their neighbors, the normal nails, also to bend, to fall out of the microtubule structure and to aggregate together. And that's called a tauopathy. When that happens to a cell, that's evidence of a diseased or dying cell. And that again would be a problem for that cell, except those cells, which are called neurofibrillary tangles, if they're in a petri dish next to normal brain cells, they can cause their brain cells to also have this process happen. And that's how tauopathies progress, the most prominent of which is Alzheimer's disease. So what we see then in response to repeated head impacts in epidemiologic studies and in vitro studies is higher rates of neurodegenerative disease, of tauopathy after repeated hits to the head, specifically those subclinical traumatic brain injuries. So we know then that repeated brain injuries at this point can cause some tau pathology. But the question is, to what extent can they manifest in clinical symptoms? But it's not just the brain injuries causing tau pathology. We also know that there's neuroinflammation that happens as a result of brain injuries that can lead to clinical symptoms. We are increasingly understanding interface astrogliosis, another process, neuropathologic process, that links brain injuries to clinical symptoms. But what we also, There we are. We also know then that these other neuropathologic processes, neuroinflammation, might increase the risk of those nails getting bent in the brain cells too. So it's all linked together. Now, Dr. Bonvie, I think, outlined this very well when we're talking about the way that early life experiences and military exposures can lead to cognitive changes. The old model, the pre-NICO model, was that you have some cognitive impairment and you go and see a neurologist. You have some pituitary changes and you go and see an endocrinologist. Hypertension, cardiologist. Disordered sleep takes you to pulmonary medicine, and chronic pain takes you to an orthopod. And all of these different specialists, even if they're the best and brightest specialists, they live in a silo. They're doing their own work in their own domain. But we increasingly realize that this is an outdated model, that pituitary dysfunction can change your brain function, that hypertension can change your brain function, disordered sleep can affect it, as can chronic pain. We also know that cognitive changes can result in changes to your heart, to your gut, to your kidneys, to your lungs, to your body, to your pain. All of these processes are linked together. And unfortunately, it becomes a very complicated process that requires an integrated approach. And then on top of that, we add problems associated with your entire lifespan. Socioeconomic status changes, changes in substance use, other personal network and saliency. All of these influence your clinical manifestation of symptoms. So what do we do then? We're already finding linkages between the changes that you'd expect to be related to brain impacts and other problems and other exposures with other health outcomes. We're finding that our SOF personnel have 3.6 times higher rates of sleep apnea, 1.8 times higher rates of thyroid dysfunction, and 2.9 times higher rates of hypertension. So how might this affect the neuroaxis? Well, heart health is brain health. So this is the brain of an operator who came and saw us at HomeBase. And I'd like to blow up one portion here. So what you see here is that little white spot on this type of image, flare image. It represents increased neuroinflammation around a blood vessel. When you think about the blood vessels in the brain, there are the blood vessels that are so small you can't see them on MRI, that are so small, in fact, that the red blood cells have to line up single file to go through them. So you can't see the changes in those blood vessels, but you can see the effects the changes of those blood vessels have on the surrounding brain tissue, and that's what we're seeing here. That what we're seeing here is damage to one of those blood vessels, and this is in a 42-year-old gentleman. I wouldn't expect to see these kinds of changes. So what could be causing that? Well, if you think about brain tissue, it has the consistency, it moves like Jell-O. And after a head impact, if you were to impact a bowl of Jell-O, it would jiggle and then it would settle down. And if you looked at it afterward, you wouldn't be able to tell that it sustained an impact. But the blood vessels in the brain have a different consistency. Think about them as like uncooked spaghetti. If you were to put that stiff, uncooked spaghetti inside your bowl of Jell-O and hit it, the Jell-O would move and the spaghetti would move, but they'd move differently. They'd respond to the impact differently. And you might, after it all settled down, see small cracks in the Jell-O around where those blood vessels are. That's what's happening after repeated brain injuries in our operators, in individuals who are exposed to blast injuries, in individuals who are exposed to hard landings and hard openings as a result of jumps. This is happening repetitively, and this is causing subclinical traumatic brain injuries that we need to understand the long-term effects of. And the problem is, for this operator, I wouldn't expect any symptoms associated with that level of white matter change, that level of blood vessel change. But it can progress. So this is another individual who you can see now there's more of these white spots that have coalesced. And you can see then that it can actually progress even further than that. And if you look, in fact, it's a little hard to see in the image here, but the folds around the brain, the folds between the brain tissue, those sulci, have widened and spread. And that's because the brain tissue itself has become so diseased that it's died and been cleared by the immune system. That's why the ventricles are so large, and that's why the folds in the brain are so large. That's what we're trying to prevent by making sure that we're treating things early. So we have all of these processes that link brain injuries to clinical symptoms. But for the most part, the pathology, the neuroinflammation, at this point, we don't have interventions that can help them. And that's where a Healthspan mediated approach is critical, because there are a whole host of other things that we can change. We can look at factors like age, sex, and race, like genetics, but also their relationship to cardiovascular disease, to pain, to disordered sleep, to diet, to cognitive reserve, substance use, exercise, socioeconomic status, stress, and social network. When I see a patient clinically, these are things I can intervene on that can adjust the linkage between repeated brain injuries and clinical symptoms, because these all are interconnected and going back and forth. And so that's what we do, because change ultimately is not universal. So this is Paul Rudd, age 52, and this is Wilford Brimley, age 52. If we can take someone who's on a path from a brain health standpoint to have Wilford Brimley brain and make them a Paul Rudd brain, then we fundamentally affected and improved their life and improved their health span. So thank you very much.